Right. So the next part is to study the discharging of the circuit. So we did the charging mode before. This is the discharging mode, which means I have moved the switch to the down position. So already the capacitor has fully charged. It's at total charge given by Q0, and now we have suddenly moved the switch to the down position, so that the only elements in the circuit now are the resistor and the capacitor. There is no source anymore. Switch is down. So once again, let us apply Kirchhoff's voltage law. So the voltage across the resistor and the voltage across the capacitor total has to be equal to 0, because there is no source of EMF this time. So once again, this is IR and this is Q divided by C. So this is R dQ by dt plus Q by C. Once again, we have a nice differential equation, linear, and it should be possible to solve this just by separation of variables. So we end up with dq over q is minus dt over rc. So when we integrate this, we get log q is minus t over rc plus some integration constant, let's call it k2. Now at t equal to 0, say we started with the capacitor fully charged, so q is q0, which if you remember from previously, this is just C times E. So then we get log Q0 is K2. So from this, putting it into the solution, we get our final result. Log of Q over Q0 is minus T over RC, or Q equals Q0 e to the minus T over RC. So this is what the charge on the capacitor looks like when the circuit is in the discharging mode. Let's plot this and see what it looks like. T, Q, this is Q0, then this is an exponentially falling function, looks like this. Yeah. So once again, RC will control how fast or how slow this discharging happens. So if RC is more, then then it takes a long time to discharge. And if RC is small, it takes less time to discharge. Yeah. Once again, we can calculate what is the current in this circuit. So this is rate of change of the charge, and what was the charge? It was Q0 e to the minus t by RC. So this current is going to be Q0 e to the minus t by RC minus over RC. Why negative? It's discharging in the opposite direction. So the current is in the opposite way. If I want to find out what is the voltage, the potential difference across the resistor, this is IR. So this is minus Q0 over R e to the minus t by RC times R C. So this is minus Q0 over C e to the minus T by RC, or minus E to the minus T by RC. Again, negative means that the potential is in the opposite way. Earlier, the direction in which the potential difference was positive, now it's the opposite way. What was more at a higher potential has gone to a lower potential. And Vc is just Q over C. So this is Q0 over C e to the minus T by RC. Once again, or e to the minus T over RC. Once again, you will find that if you add Vc and Vr, what do you get? You get 0. And this is once again Kirchhoff's voltage law, because there is no EMF in the circuit. So let us plot this now. So Vc, so if this is E and if this is minus E, then you will find that Vc is an exponentially decaying positive function, whereas Vr, so this is Vc, Vr is the same but with a negative sign. And the sum total of these two is always 0. So this is in the discharging mode. So what have we done so far? We have looked at a resistor and a capacitor in series with a DC source. And in this, we looked at the charging mode and we looked at the discharging mode. Now, we can do the exact same thing but with an inductor. So now this is LR series circuit with a DC source. So once again, the circuit looks exactly the same as before. Only thing is, instead of putting a capacitor, we are going to replace that with an inductor. So first a resistor, and then an inductor. So this is our LR series circuit with DC source. What happens in charging mode? So when the switch is up, so you have the E also in series with R and L. Kirchhoff's voltage law tells us that E should be equal to VR plus VL. VR is IR, and VL, the potential difference across an inductor, is L di by dt. Now you will see this is a differential equation in the current. Earlier we had a differential equation in the charge. Now we have a differential equation directly in the current. So you can solve it exactly the same way as we did before. And so I'm not going to do the whole calculation again because it's straightforward now that you know how to do it. What you get in the end of this calculation is I equals I0 1 minus e to the minus R by L t. Do you see the similarity with what was there before? I should define what I0 is. I0 is E over R. This is the maximum possible current that can flow through the circuit. So earlier we had almost same expression, except that it was in terms of charge, not current. And over here, instead of T over RC, now we have R over L times T. Similarly, you can also have the discharging mode. And in the discharging mode, again, now Kirchhoff's voltage law will say 0 equals IR plus L di by dt. Solve it. And in the end, you will get I equals I0 e to the minus R by L t. Now, for an LR circuit, the time constant is L over R. Just as for the RC circuit, when there is a capacitor in the circuit, then the time constant is RC. Now it is L over R. That is the only difference. Everything else roughly remains the same. So I would urge you to try out this calculation by yourself at home. Calculate, first try the charging mode, calculate what is the current in the circuit. You should get this answer. And then try and calculate what is the voltage across the resistor and the voltage across the inductor. And then do the exact same thing in the discharging mode. And plot all those voltages and currents that we get, just like we did in the previous case for the capacitor. You'll get some practice in doing this kind of calculation if you do that. Now, so far we were dealing with DC sources. Now let's try something new. Let's try not exactly an AC source, but a square wave pulse. So let's see what is the response of an RC circuit to a square wave. What does a circuit look like? Do you know this symbol? This is a symbol for a time varying source. So for an AC source, we use this kind of symbol. You might have done this in your 12th standard. So this is R, this is C, and this is your input. And I am interested in what is the voltage across the capacitor. Let's just write down once what we expect the voltage across the capacitor should be. So in the charging mode, voltage across the capacitor is, I should go back and check once. In the charging mode, voltage across the capacitor is this. And in the discharging mode, it is this, right? Yeah. So now, here comes an interesting diagram. So this is my input voltage. My input is a square wave. What a square wave means is, first it has some high value of the voltage, then it becomes low, then high again, then low again, then high again, and so on. It keeps going. So let's call this V0, and then this is minus V0. And the time period of this wave is t. So this is t by 2. Alright, and now I want to see what does Vc look like if my input looks like this. So I'm going to draw it exactly under this. Vc. What do you think is going to happen? First, when we are in this part of the wave, so this is basically like a DC source with some large voltage V0. So then this is just like being in the charging mode. So then the capacitor charges according to this formula. So it charges like this. Ideally, if this was, so let's input, output. If the input was a pure DC source, so it was just straight, flat all through, then in the output I would have increase and then gone asymptotically flat. This is what we saw previously. But now what has happened is that it comes here, but then the DC voltage stops and then it goes negative. So this means now my capacitor starts to discharge because all of a sudden it doesn't see any potential difference over there. So then it starts to follow this kind of a curve. So it starts to discharge. Once it comes here, again the input becomes high. So it's like having a source. So there it goes into charging mode again. So it again starts to charge like this. Once it comes here, again there is no potential difference across it. So it discharges. And so on. So charging whenever you are at a high input voltage, and then discharging whenever the input voltage becomes negative. Now what happens if I increase the value or if I decrease the value of RC? So let's say this is when RC is approximately the same as T by 2. But what happens now if I take a case where RC is much less than T by 2? Remember, RC is the time constant. It controls how fast or how slow the charging or the discharging is going to be. So if RC is very small, that means it's going to take very little time to charge or discharge. So the switching will happen very quickly. So we start from here and then it goes up very fast. Next, when it starts to discharge, again it discharges very fast. Again charging very fast, discharging very fast, and so on. And let's look at the third extreme, where RC is much greater than T over 2, than the period of charging discharging. Now, it's going to take a very long time to saturate. In fact, it won't even reach the saturation before it's time to switch the input. So you start from here, and then it goes so slowly, it's almost a straight line. If you had given it more time, it would have gone on like this. You can't see. If we had given it time, it would have gone on like this. But we didn't give it time because it's already time to discharge. So it starts with discharge, but again discharging is also super slow. So it just comes down almost in a straight line. And again, while charging it goes very slowly up, discharging it goes very slowly down. So here's what the potential across this capacitor looks like for various different values of RC. First is when RC is close to the time period of the input voltage. Second is when it is much smaller than it. And finally, when it is much more than it. Right?